This
Recording.
conference will now be recorded.
Okay, so tonight we're doing technical basics, and this is, in a way, if you're only going to do the foundation, a lot of this might not be. Hello, got a new one just joined us. So as I was saying, tonight we're doing technical basics. Now, if you're only going to do the foundation, you might not actually need most of this. If you go on to the intermediate, then yes, it will form a big part of the intermediate, and also of course the advanced. But yeah, nevertheless, basic electronics is part of the syllabus for the exam, and a lot of it is actually pretty simple stuff. So if you know it, you can get points in the exam, and that adds to your need 19 out of 26 correct answers. So a lot of this you might have done when you're at school, possibly even some of it at primary school, some of it maybe at secondary school. So I'm using the slides from Chelmsford Amateur Radio Society tonight. So have you read the book, the chapter 3?
Yes.
Okay, so there's basic electrical and RF symbols, units, and concepts, which I'm going to look at. So you don't need to be a circuit designer stroke builder. It does come from experience, and if you go on to do the intermediate, assuming you do the practicals when you do your intermediate, it depends, how long down the line that might be and how long the practicals are going to be suspended for. But you will do various circuits there, and you will also do a construction project as well. So for foundation, it's very simple. It's you need to understand conductors and insulators. So I just let's get this. I can't see myself here, but never mind. It's okay. I mean, so if I hold this up here, shall I take the batteries out because that will weigh it down. So if you look through this thing I put together here, the base of it is wood. What is wood?
Resistor. An insulator, sorry.
It's an insulator, yes. And then I've got a bit of paper on top of it. I've just put there for convenience sake. What is paper?
I would say that's a resistor.
Okay, good. I'll actually ask if we get someone up than Mike, because it's just good that you're an electrician. I just want to sort of get, And what about this here? Anyone know what that is? Mike?
That wire is a conductor.
It's a conductor, yes. It's not actually wire, albeit it's a wire. It's actually a piece of leaded solder. It's what I lay my hand on. And of course, you can't solder leaded solder very well without melting it. So it's just wrapped it round,
yes,
tightly to this. And screws, they're also conductors. And this thing's made out of plastic. What's plastic?
Shield.
Is it a conductor or an insulator? Yeah, it's an insulator. And you've got in here metal, that's a conductor. Of course, wire the conductors, and they're coated in plastic, which of course is an insulator. So that's but you don't need to know much about that, but apart from all metals are conductors, and obviously water is a conductor. And now there are some metals which are conductors, but which they say are poor conductors. Now, it depends what you mean by poor conductor. I mean, aluminium or steel is a conductor. I would say probably most people would say that's a strong conductor. But there are better conductors like gold and lead, for example, which are better conductors than that. But the reasonable conductor. And And insulators don't permit the flow of electrons, and they inhibit high resistance. So examples are plastic, wood, rubber, glass, and ceramics. Now, when you go on to intermediate, you will come across semiconductors and PN type material, the depletion zone. There are some conductors which will act, or some materials, semiconductors, they'll be an insulator until you pass the current gets up to a certain level, and then it will conduct, or they might only conduct in one direction. They're called semiconductors. But that's beyond the foundation course. We don't even need to know about semiconductors, but you'll go into diodes and transistors and semiconductors in intermediates. So water is a conductor, especially when it's impure. And so if I had, if this wood was very wet, for example, that could be a conductor, especially if I got high enough voltage across it. That could be a conductor. But basically, it's an insulator. But water in itself is a conductor. Air is an insulator. And resistance describes the property of a material which opposes the flow of electricity. So in the Catholic tradition, we say resistance is something that opposes the neo-modernist Rome. So we oppose the flow of electrons. So it's a slightly different thing, to what we generally refer to as resistance. And conductors are very low resistance, insulators are much higher, and resistance is measured in ohms. And we go on to electrical units now. So voltage is the potential difference. That's measured. That's probably the most common one we all know is voltage. The symbol is V. Next one is current. And now, in Ohm's law and in the PV equals VI, the power equation, then it's quite common to refer to it as I, but some people use the symbol A to refer to it. I tend to use I to remember it, but so voltage is measured in volts, so the symbol is V. Current is measured in amperes, and the symbol is A, or I is sometimes referred to it as. And resistance is measured in ohms. The unit is an ohm. The symbol is the little Greek symbol we have there for ohm, and or you can just use that as R. You could write that as, but the power is measured in watts, and the symbol is W or P. And frequency is measured in hertz, or the symbol is HZ, or we could use F for frequency. And you might have kilohertz, you might have gigahertz, megahertz, etc. Wavelength is measured in meters, which are normal meters, which we all know. But they sometimes have that funny symbol for wavelength, which might come across from time to time. So resistance is the opposition to current flow. So I suppose you could say current flow is Dr. Egan saying the word at St. Michael's School.
All in memoirs.
Oh dear.
And I was already said voltage is sometimes referred to as potential difference. The unit prefix, the millionths, you got the are micro. So you might have microwatts, microamps, microvolts. So probably static electricity could be several kilovolts, but load of only a few microamps. But So millionths are micro. So if you've got 1 million is micro, and symbol is either U or that other symbol we got there.
I move. Agree.
Got milli, which is a thousandth, so like a milliliter, for example, or a millimeter. So millions, a small m there for that. The capital M is mega, but so a lowercase m is a thousandth. A thousand is a kilo, a K, full K, but doesn't really matter there. I can't think what the big K stands for, so if I saw big K, I would assume it means the same thing there. But with M, it's different because a millions are mega with a capital M there. That's interesting. It's a small m, it's 1/1000th. If it's a capital M, it's 1 million times. So it's if it's million, it's times 10 to the power of 9, where if it's a thousandth, it's 10 to the power of -3. That's its scientific notation there. And giga is capital G, and again, I don't think that's a thing small g would stand for, but I've never ever seen a small g written, but that'd be like 10 to the power of 12, big giga. For example, here we have 4.7 kilo ohms are 4,700 ohms. So it's times 1,000. We've got 1,500 milliamps is 1.5 amps. And 0.6 megahertz is 600 kilohertz. Okay, so do you understand how that goes?
Yes, thanks.
And 500 milliwatts is 0.5 watts. So it turns out 500 milliwatts is actually the ERP, is the effective radiation power, is the maximum transmit power on PMR radio. And you might remember that in my slides last week. Just coincidence, it happens to these slides from Chelmsford Amateur Radio Society happen to state 500 milliwatts here as an example. And we've got 1,000 megahertz is 1 gigahertz. Again, if you know computers, 1,000 megabytes is 1 gigabyte. Technically, it's 1,024 in computers because they use base 2. That's outside the syllabus, by the way, but a lot of people say 1,000 anyway when it's with computers, because as humans, we work with base 10. We have 10 fingers, or other 10 fingers in the thumb, 10 digits, as they say in Latin. That's where it comes from. So whereas computers, use base 2. But anyway, for radio purposes, it's all base 10 anyway, so you needn't worry yourself about that base 2 stuff. The power is measured in watts. And here we have some examples. So you've got 10 picowatts. So it's so 50 picowatts is 50 times 10 to the power of -12, and what thing there. So you could write it in watts like that, or you could write you could also write 0. And then a load of zeros. But that's an easy way before writing the 5. But then that's another way of writing it. So RF transmit power, B is 10 watts, just the normal one there, 10 watts, which is how much used on the foundation license. Filament lamp bulb might be 60 watts, albeit, with all the climate, the political correctness thing about global warming and climate change, they use LED bulbs now, which are not good for I have Erlin syndrome, so it's not good for me. But and of course you had fluorescent bulbs before that, which used up less power, but anyway, 60 watts an example of an old filament bulb. Microwave oven, we've all got them 800 watts. Kettle 2 kilowatts. A lot of kettles might be just above 2 kilowatts, and That's important when you're working out what fuse you should put in there, what fuse you should put in the microwave, what fuse you should put in the kettle, what fuse you should put in the light, mains light. And current flowing. So current flowing through a resistor converts electrical into heat, and that can be calculated in terms of watts. Now, mentioned about fuses, it's important to have the right rating fuse, otherwise it might, excessive current could damage equipment and even cause a risk to of death potentially and injury to people. Just an example, I was working on the radio yesterday, it wasn't working, and I was trying to work out whether the diode had gone, so I shorted it out. I made a mistake and I used a crocodile clip, which I didn't check what the current rating was for it, but I assumed it'd be okay. I connected it up, and as soon as I turned the radio on, do you see that there?
Yeah.
Excessive current. It drew excessive current. It burst into flames immediately, and I turned it off. And fortunately, it's okay. I turned it off quick enough, and but you see, this wasn't capable of handling that much current, so this is acting as a resistor, and that heat, you see, which the energy was converted into, started to burn the plastic away from it, and that can be a cause of electrical fire. That's why it's important to make sure that that any cable you use is rated for is capable of carrying that current, and also fuses. Now, fuses are a safety thing, so if you put a 3 amp fuse into a kettle, all that's going to happen is the fuse is going to blow. But if you do it the other way round, let's say you put a 13 amp fuse into a 60 watt bedside lamp, then excessive current can be drawn. It's not going to have the effect it would have with the fuse. It's not. And RF power amplifiers are not 100% efficient, so some PAs may dissipate more watts in heat than the RF power output. So, for example, if I have say I got 100 watt, let's say I've got a Yaesu FT450, it transmits 100 watts of HF. Now, in order to power it, if I get 100 watt power supply for it, it runs at 13.8 volts, by the way. So, if I get 100 watt power supply, that's not going to be enough. I'm going to need to get something a bit more than 100 watts, probably about 200 watt, maybe 150 watt power supply. Now, as luck should happen, the one I've got is after it's 50 amps at 13.8 volts. That's so my one is one capable of running 400 watt transceiver, just about. But yeah, most transceivers you get are normally about most base stations are about 100 watts, realistically. But 400 watts is the maximum power I can transmit as a full license holder. Unless I get notice of variation, AK and indult from Ofcom. Which I have to have a reason for. Okay, so power supplies therefore need to be rated for the overall total power needed. So, it'd be completely mad to get a 50 watt power supply and run 100 watt rig with it. As I say, you want a bit more than 100 watt because that's the transmit power might be transmitting might be 100 watt, but I also have to run the circuitry inside the transmitter as well, and do the other things in there which are going to add up to a bit more as well. And there's different types of amplifiers, class A, B, and different, when you go on, it's in my advanced, different types of amplifiers about how RF amplifiers about what you actually need. That's beyond the syllabus, by the way. So basically, you have to make sure you have a sufficient power supply for what you're doing, what you're using it for. And here, this is one of the two formulas you're going to need. If you've got a notepad and pen, I recommend you write this down. I can send the slides afterwards as well. It should be in your book as well. P equals VI, so the power in watts equals the voltage multiplied by the current. Or if I wanted to work out what fuse, so if I was someone apart from Mike here, if I wanted to work out what fuse I could put, say I'm running something which is okay, I'm running a 900 watt microwave. The power is 900 watts. I'm running it on mains, which is 240 volts. So how am I? So what method am I going to use to work out the current of the fuse I need, or how much current it would draw?
Is it P divided by V?
Yes, so I'm going to get the power of watts, which is 900,
Oh, I see.
and I'm going to divide it by the voltage. So in the UK, it's 240 volts, or thereabout. It alternates between, I should say, 240 volts AC RMS, technically. That's, of course, RMS is intermediate territory, but I'm sure Mike knows all about that.
So you're looking at 4 amps, 3.75 I've got on my calculator.
Yeah, 4 amps, yes. So you realistically put a 5 amp fuse in that, because you don't get 4 amp fuses. You get
Okay.
you realistically, as far as I know, retail. Correct me if I'm wrong, Mike, but you would get. I think you might occasionally get a 1 amp fuse. 3 amp is common. 5 amp, 10 amp, and 13 amp. So yeah, that's what I would do if I wanted to do that. And likewise, if I was in America, I would and had 900 watt microwave that ran on 110 volts, or 150 up there, I would divide it by 110, and of course I would actually then need, in order to get that power of watts, I'd need that at a lower voltage. It goes without saying I'd have to be drawing a higher current. And obviously, if it was 110 volts and we got 240 here, it'd be more than twice the current. So you're probably looking about 10 amps, or probably about, well, it's 3.75, so you look about maybe 8 amps. You know, so I'm not sure not even sure if they have fuses in America in plugs. I don't think they have fuses on the continent in plugs. Yeah, you use the same principle anyway to work it out. So there we go. We've got the formula manipulated. As long as you know the formula and you know how to manipulate it, that's the important thing.
I'm going to have to give it some thought.
It's the same as like mass, volume, and density. You know, for various other, similar equations like that.
Yeah.
So that one, have you all got that one down?
And that triangle that you use to measure speed, distance, and time, it's the same sort of thing. It's called the Dan Silly Triangle, DST. That's how I remember my physics.
Same thing.
Same
Funny,
thing.
because I was in a GCSE maths lesson as a teaching assistant, which I was supporting, and I remember it easily as P equals VI, and also Ohm's law, which I'm going to go on to next. Okay, so don't worry, I can get down.
I've got the foundation manual. That's actually on page 5. That triangle.
Yeah.
Okay, so the other thing, then I'll go on to the next slide. So
You can see the horizontal line as the divide sign. It just makes life a bit easier, doesn't it?
yes.
Sorry.
So we so we go on now to we're not doing yoga, but we go on to Ohm's law.
Oh dear, you've got that visual now, haven't you?
I think it's becoming quite popular actually with the lockdown. You know, a lot of people are taking to it and they're doing classes by Zoom.
Yeah.
But so Ohm's law, it's V equals IR. So it's P equals VI. The V at the top now IR. So the voltage divided by the current gives you the resistance in ohms. Or likewise, the voltage divided by the resistance gives you the current in amperes, in amps. Or you could do the current in amps times the resistance will give you the voltage. And we got examples there, which same thing. So AC and DC power. And no, this is not rock band. There's nothing forbidden by the contract. It's all with contracts, they school. But yeah, they just go. But the DC is direct current. So, for example, a battery is DC, current only one direction. And AC is alternating current, where the polarity is reversed. And in the UK, that's reversed 50 times a second. In what is it? The full cycle is 50, Mike. I think it might be the full cycle. Is it 100 times a second?
Yeah.
So, and in America, I understand it's 60 hertz, the mains power. So the frequency of the AC power in the UK is 50 hertz. That you need to know for the something you might want to write down for the exam. That might be a question. So AC is alternating current is easy to generate and transform, as said there. And we use AC waveforms in radio technology. Okay, so many things will work with either AC or DC. So, for example, light bulb that'll work. Basic filament light bulb that'll work with AC or DC, but an LED won't. And an LED, by the way, is a type of semiconductor, but for the purpose of the foundation, we're only interested in it for the purpose of it won't of it matters which way around it goes. That's the hot. Even that is the furthest we're going to go into LEDs, but and the motors, for example, electric motors, if you flip the current round the other way, it will go in the opposite direction. So that way it does matter. Imagine having a remote control car with AC. They're going forward, backwards all the time. And if it just wouldn't work. So that's why we have to use direct current sometimes. And for many devices, if the polarity is the wrong way round, it will break them. And so, for example, I think of something I can break probably the wrong way around. I can get a capacitor the wrong way around that can blow sometimes. It can be fatal, but sorry, capacitors are part of the intermediate, but don't look at capacitor, but it can blow devices if you get the current the wrong way around, and that's actually one use diode. Again, that's going into intermediate territory, so sorry if I go a bit over there, but if you do intermediate, you'll come across diodes and stuff. Okay, so cells and batteries. Now these symbols you need to know for the exam. So a cell is that symbol there. A battery is two or more cells put together. If you think of it as this, I mean, this is a single cell battery. Now, if I had one of these, the proper way to do it would be to put the batteries in the circuit diagram. It doesn't really matter too much how you think of it, as long as you're that two or more cells make a battery. And it could also be a simple potential for power supply as well. But if I put two in here, then you think about that as a battery. So batteries provide a source of DC power, direct current. They store electrical energy by chemical means, and different batteries, different ways of storing it. I think that's an alkali battery, whereas this is a carbon zinc battery. I only just got this today for Wilco when I went down there, so I thought, well, I'll get one of these as well to make it more interesting. But so these are the symbols, and you might have battery packs. And if anyone's ever disassembled a laptop battery, you'll know that they've got like a load of rechargeable batteries inside them, and you can actually take them apart, disassemble them, buy individual cells off eBay, and look, some of them are a bit bigger than AA batteries maybe, and you can put them together, and you can actually refurbish batteries like that if you get it apart okay and everything like that, and save a lot of money. People on YouTube have done that rather than paying a lot of money to the manufacturer for a new laptop battery. But caution, if you do that, you need to know what you're doing. So primary cells can only be used once, so this is a primary cell here, and secondary cells can be recharged to reverse the chemical reaction, but there is a limit to how many times you can do that. It's important to avoid short circuits, and lithium and lead acid can deliver dangerous currents or overheat. You need to also be aware of leakage as well, and dispose of, this is the green bit here, dispose of them appropriately. Which I think we can maybe perhaps we respectfully disagree on that, but for the purpose of the exam, you have to give politically correct answer you're asked. Here we've got a series circuit here. We've got a resistor and a lamp in circuit, and the voltage we have here off of the battery, if we measure the resistor and the lamp, it will give us the voltage across each of them. If we measure the voltage here and here and in here, then the voltage of these two will add up to the total voltage here, the series circuit. And the current is the same all the way around the circuit. And we could work out the internal resistance of the circuit if we wanted to. Obviously, when you're measuring internal resistance, you can't just measure it with a multimeter, because the battery will have an internal resistance as well, but you can calculate it by measuring the current and the voltage. So parallel circuit, different here. So in a parallel circuit, the voltage across both these lamps will be the same, but the current at different points will be different. So anywhere from here up to here, the current will be the same, but here and here the current will be different. But the voltage will be the same at all points. The voltage will be the same across each of those, and it will be the same as you got on the battery. And we're going to do some practicals in a minute. So the supply voltage is common to all components, and the total supply current is equal to the sum of all the currents throughout each item. So the current going across that plus the current going across that would be say it's what the current the battery is supplying. And each item will have its own resistance as well. The frequency and wavelength. Now, there is also, just like Ohm's law and with P equals VI, the power equation. I think that, not sure what you, Mike, did you have a name for P equals VI when you did your training?
No, if you did, I can't remember.
I don't know what we called it either, but Ohm's law is V equals IR, and I'll just call it the power equation for now if that's okay. So you do have a way of calculating frequency versus wavelength here, and you could use this, but you're not expected to know this for the foundation, and it would be probably going a bit far. If you don't, you can if you like, but for the intermediate and the advanced, then yes, you would. This is the approach you would use. For the foundation, it's enough you get your, when you do your foundation exam, you get a foundation reference booklet, and at the back, can you see that?
Yeah.
You have a graph, and you've got wavelength in meters up there, and frequency in megahertz here, and you can look at like where the wavelength and find out or vice versa the frequency. You can read where it is, and now it's going to be A, B, C, or D. So don't worry about a margin of error reading here or there. But if or even if you have to go across with a pencil or something, or they've got loads of lines there, so you don't need to worry too much about reading that completely exactly. There'll be obvious, which will be the answer, because there'll be 4 possible answers, and you look at it, and then that's what I would say. Though is I'll send this round. It's available on the RSGB website. The reference material for use in the foundation level examination, 2019 syllabus. It's worth getting acquainted with this. You would be provided a clean copy in your exam. Now, obviously, you do your exam online, so you might have to print a copy off yourself before your exam, and then show to your invigilator that it's clean before the exam with a webcam. If any of you don't have access to a printer, and alternatively, what I can do is I can print them off myself, and I can post them to you if you can do your postal address, and I can post you hard copies of this if you like. But if you don't have access to a printer, so there's a few things there. It's probably worth getting to know. So you got the foundation license parameters, the frequencies you can use, the amount, the power output on it, and any restrictions there. You get notes on the band plans. We'll cover band plans when we do license operating procedures and licensing conditions, but band plans are not sort of statutory, so to speak. They are basically like etiquette. They're not you don't follow them. It's just considered bad etiquette not to follow them. They're sort of advisory. Got various band plans there, and then you've got on the back there you got the wavelength versus frequency conversion chart, and then you got here frequency allocation table for different types of radio. Not the amateur radio, but you got like broadcasting, aeronautical, mobile, so like what planes use and various other things. And a dB conversion table will cover dB at a future point. When we talk about antennas, and feeders, we should be covering dB then. So in the air, velocity of radio waves is consistent to that formula. You don't need to know that. But basically what you need to know is that as the frequency increases, the wavelength decreases. And vice versa, if the frequency decreases, the wavelength will increase. So for example, if I'm, say for example, I got 144 megahertz, the wavelength for that is 2 meters. If I go up to 430 megahertz, the wavelength is 70 centimeters. And if I go up to a gigahertz, then the wavelength will be 30 centimeters. You see how that works? But you got the chart there to convert it anyway when you need to in the exam. There are a few circuit symbols you need to know which are in the exam. In the foundation, they're very limited. Again, they're here, so I don't think they're all in one place in the book, but it's worth printing them out. So you've got battery, cell, hit switch you got with resistor and fuse, you need to be quite careful that they're very similar. The fuse has a filament going through it, a line going through it, all the way through the middle of it. The resistor doesn't.
Mm.
LED now, that is also similar to an LED as a type of diode. Diodes are not in the foundation syllabus apart from an LED, which is a light type of light, but the symbol is very similar for a diode. But I won't go into that because it's not in the syllabus. But we've got antenna, microphone. If you think about that vibrating across there, loudspeakers. So it might be worth actually printing this slide out and sticking it on the wall or something like that. You get to know them that way. That's what I tend to do when I revise for stuff. So I print it out and put it on my wall. I'm not sure if you can see up there, but that's some logic gates I was revising for an exam up on my wall. That's how I tend to revise myself, and then I sort of take it in subconsciously sometimes. That's part of the revision. It's not all my revision, but okay. So that's the end of that. So we'll go on to the practicals now. So just here, so I can
Talk.
see it. So I might just make that. If I can make that. There we go. It's better. Right. Get this down here. Right, so I've got this stuff put together here. So if I want to make a light bulb, but right, so anyone apart from Mike, if you want to talk, shall we just talk? Do you want to talk through what we need to do to make an electrical connection? Obviously, I know the stuff, but I want you to get you guys involved. Right, so I've got that there, and this basically is going to help us connect it up. I bought these crocodile clips recently for this, so it should make things easier. I have got some normal wires and a screwdriver for some of it if we need more. Right, so basic bulb, yeah. I might just to start with, and I'm actually going to short out one of these here because I just want to do one cell. So if I put one cell in here.
What's the voltage you're putting on at the moment, Antonio?
Just one AA battery.
Yeah.
Just 1.5. So that's, see what I've
One
done there,
in 1 amp, Antonio.
No, it's not 1 amp. We can measure the current actually, and we'll see. I've got a multimeter, so I've got the positive and negative there. You see, I've I'm going to be collecting quite a lot of light bulbs up in due course, and we're going to connect them up and sit in series and in parallel. And right, so if I connect up for apologies about the camera, by the way. Do let me know if I can help at all by moving the camera. So now I'm not going to put those together, we'll have a short circuit. But if I connect, again, it doesn't matter which way around, put it on the, with normal bulbs. If I connect them up like that, we should have, oh, I know why we've got too much, there we go. I'll put it onto the lead because lead is better conductor than, so here we go. We got one bulb here. It's not very bright actually, but that's basically one bulb connected up. Now, if I want to make it brighter, what can I do? Okay, so I've got a bulb connected up there. It's not very bright. What can I do to make it brighter?
Put another battery. Well, yeah, put another battery in there.
Okay. Good. So I'm put another I'll take the short lead off. I'm going to put another battery in there now. Put another battery in, yeah.
Oh,
And why isn't it working?
Is it because the battery's not bubbly?
Correct, yes, the battery is the wrong way around. Have you noticed that, by the way? I did that deliberately just to see if you notice. You see, batteries have to be wired the right way around when you connect them together. It's no good putting, it's no good if I just it's no good putting them like two like that, two positive to positive and then one negative, or two like that. They have to be positive to negative. Put them in series. I mean, you could put them together, you know, like that, and have them in parallel, which wouldn't increase the voltage, but I mean, the glass will get more current out of them, but be able to draw more current. So yes, now I've got two batteries now connected in series, and one light bulb connected. It's now a lot brighter. Do you notice that's a lot brighter? Okay, so now I'm going to add now another bulb to it. So how do I wire up another bulb to this?
no idea.
Okay,
Parallel or series?
okay, let's, for the time being, we'll say series, shall we? So, sorry, this is easy to get. So we got, I'll show you what we got so far for the one bulb. It might help. So we got battery battery pack there, positive and negative. We got two conductors, a positive conductor here, negative conductor there, and to each of them we got positive, negative. You see I've labelled it here, and then connected up there to one light bulb. So I've got another bulb here. So, and I've got another crocodile clip here. What do I do to connect it up? So I've got two bulbs going.
Place it in between both bulbs and separate. So separate the lead and add it in between. The black lead goes in between both bulbs.
Okay. All right.
If that makes sense.
And you'll see what happens when that happens when I do this. And,
Can't see it.
sorry, so I'm just connected it up now. So there we go. So I've separated that there, and now
Has it gone off? Yeah, I can't see. Oh yeah.
Yeah, I'll connect it up now. Okay, I've done that, but do you notice they're both on, but they're both dimmer?
Yeah.
Okay, so what can I do now to make them brighter? And here's the thing, I only have, I've been told, imagine I've got a task, I've got to make them brighter. I've only got one crocodile clip to make it brighter. What can I do?
Use the red battery, the larger battery.
I don't have another battery. Let's say I don't.
Okay. In that case,
Parallel?
Oh, okay, we could actually, I do have a large battery for the first list. We'll get to that a bit later. So yeah, we could do that. So if I take these out, if I connect up a higher voltage battery, I could increase the voltage. And if I increase the voltage, I'll take those out and I'll connect up the 6-volt battery. That has 3 volts there going through it. So I'll connect this one up now. It's actually, if I could track valve, somehow put that on there. So,
Oh, this is really bad camera.
so if I, right, yes, so here we go. So I've connected that now to the 6-volt battery, and they're now both on, they're both bright. Okay, so far so good. Now I'm going to, but 2 bright bulbs is not enough, so you know what I'm going to do now? I'm going to add 2 more. We'll see what happens when I add 2 more from the 6-volt battery. So if I put it there, that's probably going to be. So that's balance that camera there. That's I can balance that. There we go. So if I add 2 more now, so I'm going to do the same thing. I'm going to disconnect this lead here. I'm going to plug that one into there. Yeah, I'll just add 1 more for the time being, then I'll add another one. So I have 3, and then I'll just show you what it looks like 3. So, right. Okay, so that's the brightness with 2 there. Of the 2 which are lighting up. If I get a good look at that brightness, I'll show you what it's like with 3. If I connect this here, you notice the brightness has gone down. So it's 3. If I go back to 2, that's 2. If you look at those 2, 3, 2, 3. The brightness has gone down already. If I add another one, because I don't want to blow bulbs too soon, but we will get on to blowing bulbs later. Get another one here. If I get, and now I'm going to connect. So there we go. I've got 4 bulbs there. Can you see all 4? I've got 1, 2, 3, 4. If it works right, can I? Sorry, can I? So I've got 4 bulbs, yeah. That's so that's the brightness with 3 bulbs. And if I go up to yeah, so you got all 3. If I go to 4 bulbs, see the brightness has gone down.
Yeah.
So if I show you, that's 2 bulbs, 3 bulbs, 4 bulbs, 2 bulbs, 3 bulbs, 4 bulbs. And the reason is because every time I do this, it's dividing the voltage by the number of them if I do it in series. And I can actually prove that to you here. I've got a multimeter, and if I can adjust that so that you can see that. I'm not sure if you can. I can. Oh, I don't know what I can do that. Some sort of prop. So a DOD prop with the whole camera. Right. Right. So the multimeter. If I connect that up to connect it up to this one, so we've got 2 bulbs. If I put that temporary on there, and if I measure, you see that one is on. If I measure the voltage, you can read the multimeter now. If I measure, so we've got 2 bulbs of light. You can see them just about on your screen. I think 2 bulbs. If I measure the voltage across, sorry, I come around there. If I measure the voltage across there, you see it's pulling. Well, there's a bit of resistance in the circuit. It's pulling 2.5 volts with 2 bulbs. 2.5 volts here, thereabouts. Give or take a bit of resistance. If I measure the battery at source, I'm actually going to put this directly onto the battery now, the 6-volt battery, which I measure that at source, yeah. Put them on there. So you see that's just, sorry, it's 6 volts. There is resistance obviously in the circuit there with the probably poor connection here, but 2.5 volts, 2.5 volts. That's with 2 bulbs. When I add another bulb to it, just take that off now. So if I add a bulb to it, so we have 3 bulbs. Take that one off. So we had 2.5 volts before on each bulb, thereabouts. Now the resistance in the circuit here is actually quite high, probably because of the bad connection. Because I haven't soldered anything on; it's just a touching connection. But so now if we look at you see that still. So I'm now going to. So we got 3 bulbs, yeah. Going. If I measure it now across the voltage across here, you see that we got 1.63 volts. Got 1.71. It's about the same, give or take a bit. Obviously, resistance, and this multimeter is a cheap multimeter as well. What's going to happen now when I add a 4th bulb on?
The voltage will drop again.
Yeah, okay, so let's see if that happens. So we've got all 4 bulbs there, like the 4 bishops. Nothing wrong with having more bishops apart from bishops where they get a bit political. And more potential for that, you know, in a way. But then suppose you could argue by having less, you know, I mean, if every speaker was also a bishop, then maybe there'd be less occasion in politics in terms of, you know, Bishop Sanborn and the like, but, you know, it's, I don't think this webcam's meant to be focusing down, sort of, but having to sort of improvise. But yeah, we have got 4 there. That's got 1, 2, 3, 4. 1, 2, 3, 2. Let's see. There are 4 there. So yeah, there's. It's not showing on screen, but I got 4. Yeah, 1, 2, 3, 4, and right, they're all on screen. But if I now, there are 4 there. You've seen that. So just put the volt multimeter in view. Put it on 20 volt. So setting. So if I now measure it across here, oh, okay. So you can see it first. Oops. There we go. I'll just put it across here. What are we getting? What are we getting for? Is it 1.63 or something? 1.26? 1.22? 1.28? And 1.23. Okay, with that being said, if I want them to all go brightly, what can I do? I've got no more batteries. What can I do?
You could add another lead in between the positive terminal, say, and the last battery, sorry, the last bulb, and then that would provide power back the other way. I think that's how it works, isn't it?
I could put them in parallel, yes. Now, obviously, that's an option. So if we look at how bright they are now, think about that. Now, I'm going to put them in parallel. I'm actually going to put them in parallel with 3 volts with these AA batteries, and they should be brighter than what you get here, all 4 of them, if I put them all in parallel, which is why I've got a whole load of screws in there, so I've put them all in parallel. If I just assemble that now, so that. Actually, I can keep some of them on. Yes, so right. So I'll put the batteries back in there. And have a look at see if we've actually got much resistance in there, are we? Right, so if I just
So this means all the bulbs will be getting a direct connection each.
there will be, yeah. So if I put that down there, so if I on there, so yeah, I'm getting 2 points. All right, I'm actually getting 2.94 volts here. 2.94 volts. If I go to the LED here, yeah, so it's connection's a bit finicky here, so that's why I'm getting a bit of resistance here and there, and it's a bit sporadic resistance. 2.94 volts. If I go right to the source, I'm getting about the again, that's the polarity. See, if I put it that way round, it's showing up as if I put the positive is red and negative is black. If I were to just for around, so you get that's what I mean is it's the bad connection. But there we go. See how much that connection can make. See if that's a bad connection. You see if that's what wasn't. That's what I mean. Anyway, so you've got 2.94 volts there, yeah. And now if I connect these all together, all up, so there's parallel. I'm going to use them in pair the colours just so for ease. So if I connect that one up, if I connect the red one up, call this one the red one. That one comes on. If I connect the green one up now, I'm going to call it the green one. I'm going to refer to them by the colour of the crocodile clips, just to make it easier. If I connect the green one up, the green up to, you see there, it's still the same brightness. Okay, the yellow one up. See, that is getting a bit dim. I think that bulb's on the way out. That's why it's. I'll just change. Shall I change that? Sorry, might be on its way out, but yeah, it's getting the same. Right, so I set the. There you go. So it's still the same brightness for free, despite using, you know, the fourth one finally, the white one. So you see there, we've got all four now, we're connecting them in parallel. So what should the voltage be across any of these?
The same.
And,
2.94.
okay, let's measure it and see.
2.94.
Okay, so you can see it there. So fine now. That's 1.94. It should be 2.94, but let's just check. I'll check what we get off here. Yes, so we're getting 2 volts off here. We're getting, again, there's a bit of resistance as it comes down here, and also when you pull, we're also pulling more current, so the voltage does tend to drop when you pull a bit of current sometimes. And again, you see this.
Battery's running down a bit, probably, yeah?
Yeah, possibly, yeah. It could also be that these, yes, I say, actually, you notice that that's connected to aluminium, that bulb here. What happens when I connect it to the lead? It gets brighter. You see, lead is better conductor than metal, than aluminium or steel. These are probably stainless steel, these screws. If I connect, or let's see what happens. If I connect it up to the lead, rather than connecting it to the screws, I'll connect it to the lead and solder, because lead is a very good conductor, much better than aluminium or steel. It's passing through the lead anyway, but this way it's reducing potential for resistance. See there? So if I now measure across here, I'm still only getting 1.9 volts, but we get one. You see what I mean? These bulbs are actually rated at, yeah, the battery is probably wearing down. You know what I'm going to do now is, for a bit of fun, I'm going to connect these up to 6 volts. Now, they should go, these bulbs are rated at 2.5 volts. I think they probably will go at 6 volts, but they might be risking to blow, but they're not that expensive, so I'm willing to take that risk. So I'm going to connect them up now to the 6 volts, see what happens. So
You got your safety glasses on, Antonio?
these cover me anyway. I'm going to be running a higher voltage than that shortly. So, and onto there, make sure it's correctly. And then okay. It's really bright, Steve.
Yeah.
If I measure that now, I'm not sure if you can see that. It might be so bright you have problems seeing that, but let's give it a go anyway. We're getting of course we've got resistance here, but that's getting 3.92 volts across those. Again, we've probably got quite a lot of resistance in here because of all the currents travelling through this, and that's probably what it is, and the resistance is actually causing that. But now for the fun part. This is the really fun part. Right, that there.
Leave the camera somewhere else.
So no, there we go. Right, yeah, just need these to do this with. So I'm going to crimp this here because right, that'll hold.
Oh,
I just need to hold this here, so I'm just connecting that there. So right, I've got below here
oh, what's happened?
a transformer, and this converts AC to DC. If I be set to, I mean, just it goes adjustable voltage anywhere between 8 volts and 16 volts. You can turn it on now. You see that?
Yeah, you've blown them on.
The bulbs just went. Did you flash?
What voltage was that set to, Antonio? 8 what?
8.08. Now I'm not going to. That's 4 volts below. I'm going to. For those who missed it, now I'm going to blow one more just by itself. I'm not going to blow enough for 4, but that was. I'm going to blow one bulb. I might do 2 actually. I might max up. So 1 bulb here. Okay. You ready? That focused.
Yeah.
There we go. And now what I'm going to do is, there we go. We'll go up to 15 volts actually, but I turned it off now, and I'm going to put in another bulb, and I'm now going to blow one up at 15 volts. So right, we're at 2.5 volts. So right, I might actually get there. Right, ready? Right, 3, 2, 1.
You found
There we
it.
go. That's very keeping with Lodato C. 6 bulbs blown. I'm sure Begonia will be pleased with that.
Oh dear.
But yeah, so that's what happens if you put too much high voltage across a bulb. It's actually interesting because I did actually connect one up to a battery, and it did actually take 6 volts. In fact, a proper 6 volts. In fact, just to prove that, I'm going to connect one of these up to a battery now, and I can spare a 7th bulb, I think. But yeah, I've got plenty of bulbs, so take the yellow one, and I was rather hoping it would take more than that, but yeah, 8 volts is enough to blow the bulb, 2.5 volt bulbs. So before I take these off here. Right, so here we go. Just the one there to the the battery now. There you go, that's 6 volts across it. It'll take 6 volts, probably not for very long, but let's see if I can measure that now. And I'm getting 5.53 volts. Actually, it's probably not a very good battery, to be honest, a 6 volt battery. Oh, it's just blown, you see. It lasted, what, how much, that 10 seconds or so? Was it 20 seconds?
Yeah.
6 volts at 20 seconds or so, it'll just blow it. And that's what happens, you put too much current, too much power across it, it will draw too much current. See, when you put the voltage up, the voltage leaves the current. Sorry, that's getting a bit too technical. And it'll pull too much current and it'll melt the wire in the filament wire in the bulb. Anyway, that's technical basics for tonight. Is there anything that right, next week I'll just see what we right, so it's about 10 minutes before you got to go, haven't we? So yeah, I've done the plan now. I reckon it's going to take us about 9 weeks to get through the foundation stuff.
Yeah.
How many? 9?
I reckon about 9. It depends, but I think we've
Okay.
probably everything on technical basics we need to cover. So next week I think we'll cover propagation. Now we might go into a bit about transmission this week as well as propagation, but propagation should be pretty short. But propagation is chapter 7, which is pages 17 and 18, just 2 pages. And I've already talked about already. So if you want to do that for your homework, and then if you want to read about transmitters and receivers, then look that up. So see, yes, the transmitters is so propagation is page 17 and 18. And then if you get time after that, transmitters is page 9 and 10. Receivers is page 11.
Okay.
Has anyone enrolled on the Essex Ham Foundation online course?
We haven't enrolled on that yet.
No, I
No, not yet.
So
Not
feel
yet.
free to sign up if you like. They might do things in slightly different order. I mean, I'm quite happy to be flexible and adjust to what your needs are. But as long as we cover the material, that's the important thing. And I want to put you in a position where you're going to pass the exam with ease. And it is a pretty, if you read the book and stuff, in a way, it's a pretty hard exam a pretty easy exam to fail. Sorry, pretty hard exam to fail, so to speak. I mean, if you go into it nothing, then you probably would fail it. But, I mean, it is basic 8-year-olds have passed it, so it's don't you get too worried about it. But yeah, there is a bit of a queue for exams as well. But I reckon we might get exams about July or so, the way things are going, because the RSGB are already booked up for June exams, and I think on the 1st of June they're going to take bookings for the July exam dates.
Yeah.
I'll let you know when I know any more, but I got an email the other day to say to that effect, but I've got to just check that out find out what the link is to the website. They're going to make it so you book your exams online for the RSGB website, by the way, and that's opening up on the 1st of June.
Okay.
So presumably the web page will be there on the website on the 1st of June, but I'll let you know when I know.
Thanks, Antonio.
So you're looking at July for exam at some point during July.